Wow, space weather fans, get ready for some excitement. Our very own star, the Sun, has just done something spectacular. It has unleashed a significant solar eruption. We call this a coronal mass ejection, or CME for short. Think of it like a giant cannonball of solar stuff shot out into space. This particular CME is quite impressive. It originated from a very active region on the Sun. These regions are often crackling with magnetic energy, and this time that energy was released in a big way, sending this cloud hurtling towards us. This massive cloud of solar plasma is now on a journey. It is traveling at incredible speeds through the solar system. Its target? Well, our home planet Earth is right in its path. Scientists have been tracking it carefully since it left the Sun. They use satellites and ground-based instruments to watch its progress. The energy packed into this CME is substantial. It carries with it parts of the Sun's atmosphere and its magnetic field. This makes it a very interesting event for us to study and observe closely. So, what does this mean for us here on Earth? When this CME arrives, it will interact with our planet's natural defenses. Earth has a magnetic field called the magnetosphere. This field usually protects us from the constant stream of solar particles. But a big CME like this one can really shake things up. When this CME, this giant cloud of solar particles, reaches Earth, it doesn't just pass by quietly, it slams into our planet's magnetic field. This magnetic field, our magnetosphere, is like an invisible shield. It usually deflects the solar wind, which is a constant stream of particles from the Sun. But a CME is much more powerful than the normal solar wind. It's a concentrated blast. The impact can cause our magnetosphere to wobble and shake. This disturbance is what we call a geomagnetic storm. These storms are rated on a scale, much like hurricanes. The strength of the geomagnetic storm depends on a few things. It depends on the speed of the CME. It also depends on the density of the particles in the cloud. And very importantly, it depends on the direction of the magnetic field embedded within the CME. If the CME's magnetic field is pointing south, opposite to Earth's northward pointing magnetic field at the point of impact, then things get really interesting. This allows for a much more efficient transfer of energy. It's like opening a door for the solar particles to flood into our upper atmosphere. This is when we can expect stronger storm conditions. During a geomagnetic storm, our planet's magnetic field lines get stretched and then snap back. This process accelerates particles already trapped in the magnetosphere. Get ready, Aurora hunters, because this is what you have been waiting for. The incoming CME and the expected geomagnetic storm mean one thing for sky watchers: auroras. We are anticipating a potentially widespread and vibrant display. The strength of the geomagnetic storm is often measured by the KP index. This index goes from 0 to 9. A KP of 5 indicates a minor geomagnetic storm. A KP of 6 or 7 means a moderate to strong storm. And KP 8 or 9 signifies a very strong to extreme storm, which can produce auroras visible at much lower latitudes than usual. Current forecasts suggest that this storm could reach G3 strong or even G4 severe levels on the NOAA space weather scales. This translates to a KP index likely reaching 7 or perhaps even 8. This is fantastic news for aurora visibility. When the KP index is high, the auroral oval expands. The auroral oval is the region around the Earth's magnetic poles where auroras typically occur. A higher KP means this oval gets bigger. It stretches further towards the equator. This means people in regions that rarely see the northern lights might get a chance this time. The colors of the aurora are also fascinating. The most common color is a beautiful green. This is caused by energized particles colliding with oxygen atoms at altitudes of about 60 to 150 miles. To catch the best view of these amazing auroras, timing and location are key. Generally, the best time to watch for auroras is during the darkest hours of the night. This is usually from about 10 p.m. to 3 a.m. local time. During these hours, the sky is at its darkest, assuming there is no bright moon. This allows the fainter auroral light to stand out. The peak of the geomagnetic storm, when the KP index is highest, will offer the most intense and widespread displays. So keep an eye on the real-time storm data. Finding a good location is just as important as the timing. You want to get away from city lights as much as possible. Light pollution can wash out the auroras, especially if they are not extremely bright. Find a spot with a clear, dark view towards the north if you are in the northern hemisphere. For those in the southern hemisphere, look south. A location with an open horizon like a field, a lake, or a hilltop is ideal. This will give you an unobstructed view of the sky where the auroras are most likely to appear. Patience is also a virtue. Sometimes the aurora can be faint at first and then build in intensity. Remember to dress warmly. Even if it's a summer night, standing outside for a long time can get chilly. Bring a comfortable chair or a blanket to lie on. Allow your eyes to adjust to the darkness for at least 15 to 20 minutes. While the prospect of seeing brilliant auroras is incredibly exciting, there are a couple of common Earth-based obstacles that can spoil the show. The biggest culprits are, of course, clouds. If your local weather forecast calls for thick cloud cover during the peak storm times, unfortunately, you won't be able to see the auroras, no matter how strong they are. The auroras happen high up in the atmosphere, far above the clouds. So a clear sky is absolutely essential for any chance of viewing. Check your local weather forecast frequently as the event approaches. Another potential viewing challenge, especially in recent years during certain seasons, is smoke from wildfires. Large plumes of smoke can drift for hundreds or even thousands of miles. This smoke can create a hazy sky, significantly reducing visibility. Even if the sky isn't completely overcast with clouds, a thick layer of smoke can obscure the relatively faint light of the aurora. It can make the stars look dimmer, and can certainly make it harder to spot those delicate green, red, or purple hues. So, check air quality reports and smoke maps for your area if this is a concern where you live. What can you do if clouds or smoke are threatening your aurora viewing plans? If you are mobile and determined, you might consider driving to a location with clearer skies. Check weather satellite imagery and smoke forecast models. Sometimes even a short drive of an hour or two can make a big difference. Look for areas that are predicted to be clear during the prime viewing window. This takes some dedication, but for a potentially strong aurora display, it might be worth the effort. You don't have to be a professional scientist to follow this space weather event in real time. There are many excellent resources available online and through apps that can help you track the geomagnetic storm and aurora forecast. One of the best places to start is the Space Weather Prediction Center, or SWPC, run by NOAA, the National Oceanic and Atmospheric Administration in the USA. Their website provides up-to-the-minute data on solar activity, the solar wind, and forecasts for geomagnetic storms. They issue alerts and warnings, which can be very helpful. Many smartphone apps are also dedicated to aurora forecasting. These apps often use data from SWPC and other sources. They can provide notifications when the KP index reaches a certain level. They might also show you the current position and extent of the auroral oval. Some apps even have user-submitted reports so you can see if people near you are spotting the aurora. Popular apps include names like My Aurora Forecast and Alerts or Space Weather Lab. Search your app store for Aurora Forecast and you'll find several options. These tools can be invaluable for knowing when to head outside. When you are looking at the data, pay close attention to a few key things. The KP index, as we've discussed, is a great indicator of overall geomagnetic activity. Look for values of KP5 or higher for a good chance of seeing auroras at mid-latitudes. Another important parameter is the BZ component of the Interplanetary Magnetic Field, or IMF. If the BZ is strongly negative, or southward, it means more energy is being transferred into Earth's magnetosphere, leading to stronger auroras. This current solar event, while exciting, is part of a long history of the Sun interacting with Earth. Our star has been sending out CMEs and causing geomagnetic storms for billions of years. Humans have been observing and recording auroras for centuries, often attributing them to spiritual or mythical causes before we understood the science. Ancient Chinese, Greek, Roman, and Norse cultures all have records of spectacular celestial lights. These historical accounts help us understand the frequency and intensity of past solar storms, even before we had scientific instruments. One of the most famous historical solar storms is the Carrington event of 1859. This was an incredibly powerful geomagnetic storm, perhaps the strongest in recorded history. Auroras were seen all over the world, even in tropical regions like Cuba, Jamaica, and Hawaii. Telegraph systems, which were the high-tech communication of the day, experienced widespread disruptions. Operators received electric shocks, telegraph paper caught fire, and some systems even continued to operate with the batteries disconnected, powered by the induced currents from the storm. It was a dramatic demonstration of the sun's power. More recently, there have been other significant storms. In March 1989, a strong geomagnetic storm caused a major power blackout in Quebec, Canada. millions of people were left without electricity for many hours. This event highlighted the vulnerability of modern power grids to space weather. It spurred a lot of research and improvements in how we monitor and prepare for these solar onslaughts. There have been other notable storms in 2000 and 2003, known as the Halloween storms, and 2015, each producing widespread auroras and some technological impacts. The sun's activity, including the frequency of solar flares and CMEs, is not constant. It follows a roughly 11-year cycle, known as the solar cycle. During this cycle, the sun goes from a period of low activity called solar minimum to a period of high activity called solar maximum, and then back to minimum again. We are currently in solar cycle 25. This cycle began in December 2019, and we are now approaching or are in its maximum phase. This means we are seeing an increase in sunspots, solar flares, and consequently, more CMEs directed towards Earth. This is fantastic news for aurora lovers. During solar maximum and the years around it, the chances of experiencing strong geomagnetic storms and widespread auroral displays are much higher. The sun becomes more energetic, with more complex and unstable magnetic regions on its surface. These are the breeding grounds for the eruptions that cause space weather. So the event we are anticipating now is part of this larger pattern of increasing solar activity. We can expect more opportunities like this one in the coming months and couple of years as solar cycle 25 continues to be active. Each solar cycle is different. Some cycles are stronger, with higher peaks of activity, while others are weaker. Scientists are still working to understand exactly what drives these variations. Solar cycle 24, the one before the current one, was relatively weak compared to previous cycles. Early predictions for solar cycle 25 suggested it might also be on the weaker side, similar to cycle 24. However, so far solar cycle 25 has been outperforming those initial forecasts.